So this is where we left off in the last video, that if we add a multiple of one row to another row, it doesn't change the determinant. Okay? And we're going to use this property to demonstrate another property. And this one says that, okay, if a matrix contains a row of zeros, then its determinant is 0. Okay, well, let's set up a 3 by 3 here. And let's put a 0 row in the second row. And let's put GHI here. Now, what I'm going to do here is I'm going to do that row operation, that adding a multiple of one row to another, because that doesn't change the value of the determinant. And what I'd like to do is, so the second row is going to change to the second row plus 1 times the first row. And if we do that, we can say that's equal to this determinant. And we have A, B, C twice. Now we've seen earlier that if a matrix contains the same row twice, then its determinant is 0. And so this determinant is 0, so the original determinant is equal to 0. So that's a pretty quick proof of this property. Alright, this next one's really useful because it has a practical consequence. And so it says that if you have a triangular matrix, then you can find its determinant by just multiplying the diagonal entries. Okay, and I'm saying triangular, and so upper triangular or lower triangular is okay. So just to jump ahead here to this consequence, so you know that a diagonal matrix in particular is both upper and lower triangular. So in particular, it's a triangular matrix. So I can get the determinant of a diagonal matrix by just multiplying the diagonal entries. Okay, so let's take a look at, let's do a lower triangular. So let's set up, let's see here. So I'll have x, y, z on the main diagonal, and I'll make a lower triangular matrix. So I'll put zeros there, and here I'll put A, G, and H. Okay, so what I'd like to do is I'd like to perform a sequence of row operations, and I'm going to do it in such a way so that the determinant doesn't change. And again, the row operation I'd like to do is add a multiple of one row to another row. Now, my goal is to eliminate these 3 entries. I want to turn these into 0. Okay, so starting with A, what I'd like to do is I'd like to change the second row by taking the second row and adding a multiple of the first row, and the correct multiple is, of course, negative A over X times the first row. Okay, and if I do that, then the first row doesn't change, the second row will be 0, Y, 0, and the third row will be GHI. And now what I'd like to do is I'd like to eliminate this, make it a 0. So I'm going to do a similar row operation. I'm going to say, okay, change the third row by third row plus a multiple of the first row. And of course the correct multiple here is negative G over X times R1. And if I do that row operation, again my determinant stays the same. So I can write equal there. 0y 0 and then 0 hi. And now finally, I'm going to do something similar to eliminate h. This time I'm going to use the second row, so I'm going to take the third row and add a multiple of the second row, and the correct multiple here is negative h over y times the second row. Okay, so then I have, this is equal to x 0, 0, 0, y 0, and 0, 0. I think I've made a mistake here. I think these should, I called this a z earlier, didn't I? Yes. Let me change that real quick. There we go. Z. Okay. Great. So far, the only row operations I've done is this one over and over again, so the determinant didn't change. Now, we're going to use linearity, and we're going to use it 3 times. So the first thing we're going to do is we're going to factor out x from the first row. We get 1, 0, 0, 0, y, 0, 0, 0, z. Now we're going to use linearity again and factor out y from the second row. So I get 1, 0, 0, 0, 1, 0, and 0, 0, z. And I'm going to use linearity one more time. You probably know what. We're going to factor out z from the third row. Oops. And what we have is finally a matrix whose determinant I definitely know, because it's the first property in the defining properties that the determinant of the identity matrix is 1. And so there we are, x, y, z. And that's really what we're trying to do. Let's go back and read the property again. If a matrix is triangular, then its determinant is the product of the diagonal entries. So I can just take this diagonal entries, and the product of those 3 values is what we get as the answer of the determinant.